All right, so as we continue to work with rotational motion and angular velocity, we're going to lead into talking about something called torque. And so torque is the force needed, right, to get something to start rotating. And you can see here, it's really just a perpendicular distance from the axis of rotation. So that's in this case of a door, it would be the hinges, um, to the line along which the force acts. So, for example, if you try to push a door open here, the torque would be related to the distance here to the force you apply. Or if you try the handle, it would be the distance here to the force you apply. And the positive direction and negative direction, of course, is there too because force is a vector. But torque allows the force needed to to get an object to start rotating. And again, it's from the center of rotation, or the axis of rotation. So the idea is that the longer the lever arm is, the easier it should be to rotate objects. You see the pipe wrench here, and if you've ever done any kind of plumbing, you know what I'm talking about. Or even here, lug nuts on a car tire. Okay, so just keep those things in mind. That longer lever arm is very helpful. So let's take a look here at different forces that we could apply. So lever arm is this distance, right? And it's the same. It's RA in this case. Um, the lever arm for force D is 0 because it's going to be going in the opposite direction. So if I'm applying a force this way, obviously the door is not going to move. The lever arm for A is going up, so my force is going this way, so my axis of rotation is going to rotate like it should. But then let's say I push at an angle, all right? So now when I push at an angle, I'm not using this axis of rotation. I'm using this, which is perpendicular line, okay, to my force. And that's how I can find that. Um, so if we have all these forces acting at once, obviously this one's going to be 0, but these two will work together then to get the door to go, if you will, okay? So RA doesn't only applies when we're perpendicular. If we got an angle, we have to have the line of action to get the actual radius that we're going to use to find the torque that we're applying, okay? So torque is radius, this perpendicular radius distance, okay? That's hard to say. Perpendicular radius distance of our force multiplied by our force. So force times distance, torque, right, would be work. So here we go. So we're bending an elbow, okay? We do 700 newtons of force to bend that elbow. And you can see that the muscle is 5 centimeters away. So if we take 5 centimeters, which we convert to meters times 700, that will tell us the torque in our elbow. Now let's say we're at an angle, okay? And we want to see the torque after we bend our elbow some, all right? So we got to find one perpendicular, okay, which would be here. So we're looking at our axis and the distance here, and our angle 60. So this would be our radius, and then our force would be the 700 newtons. So to find that radius, we would have to take our 5 centimeters, right? And then this would be our hypotenuse of our right triangle, because our right triangle here, our right angle's here. So then we'd have to solve for that, okay? Solve for R using trig, and then take that R times our force, and that would be the torque at that angle. So here's something, and again, we're going to do the math with that. I just wanted to show it to you. So biceps torque. The biceps muscle exerts a vertical force in the lower arm bent as shown in these figures that we saw before. For each case, calculate the torque about the axis of rotation through the elbow joint, assuming the muscle is attached 5 centimeters from the elbow as shown, okay? Do it now.
All right, so biceps torque. We've got two situations. I'm going to call this A and B. I think they called it
Good afternoon. This is a student page for Ariel Galliaro.
C and
Please
D
report to the library at this time.
on the
Thank
assignment.
you.
So, but it doesn't matter. I mean, well, the math will be the same. So, in A, the force is given. So we know our force is 700 newtons, right? And the radius is 5 centimeters, which will equal 5 centimeters, so it's what, 0.05 meters. Okay, so we have our radius and we have our force, and essentially torque, right? Torque, I think we said, yeah, is equal to the perpendicular radius, right? And times the force. So right here is going to be what we're talking about, okay? But since we're going to be on a nice plane here, we're just looking at as it's torque through the elbow joint, assuming the muscle. Okay, yeah. So we're just looking at it when it's right here like this. So we're looking at this right here. So our radius is 0.05, and our force is 700 meters. So torque here is going to be about as simple as it gets. I do all this and I get 35, right? And it's meters times newtons, newtons times meters. I guess I'll go in the order that I have it set up, but this is my torque when the elbow is like this. Now we're talking about the elbow being bent, right? And you saw the picture. The elbow's being bent, so instead of being here, it's going to be down here, 60 degrees, and or 30 degrees, then we're going to look at the torque. So we drew it up with the free body diagrams, and we're trying to find then what the torque is. And to find this torque, we take our radius, which is still the same, 0.05 meters. But now when we talk about the force is going to be at an angle, and our force is going to be at an angle that's related to 60 degrees. So it's going to be 700 times the sine of 60. Sine being opposite. Remember, this is 700, and we're trying to find this force here. So this is what we're going to say. So we're keeping this is our radius, right? Then this is our force that's going to be perpendicular to it. So we're taking 700 times the sine of 60 to get that force. So 0.05 times 700 times the sine of 60 gives us 30.3 meter newtons. And we can see that there's less torque at an angle than there is here. And you might be able to feel that when you move your elbow up and down. You can see as you take that angle and bring it up, you can start to feel a little bit more in here, and that's the torque that you're feeling.
And then the more common torque problem would be something like this. Two forces, 20 newtons and then 30 newtons at an angle, are applied to a meter stick, which can rotate about the left end. So here's our axis of rotation. Force B is applied perpendicularly at the midpoint. Which force exerts the greater torque, A or B, or both the same? Do it now.
All right, so I tried to reconstruct this. We have one force of 20 newtons being pushed right smack dab in the center of this stick, and then we have another force at 30-degree angle that's 30 newtons being pushed this way. And they said this is at the midway point and this is at the end. I randomly chose 5 and 10. I mean, you could use any numbers. You can use 1 and 2, whatever, to solve this. And so the torque here is pretty simple, right? It's going to be 5 times 20, or 100 Newton meters, or meter newtons, depending on what you're doing here, right? So 100 is the torque in the center. So now we want to see what this torque compares. Remember, it's got to be perpendicular. So we're gonna look at that part, which is opposite, right? So it's going to be sine. So our torque is going to be our distance, 10, multiplied by our force of 30 times force of 30. How about that? Times the sine of 30, which will be this component that's going to be perpendicular to our surface, right? And so we'll have to calculate that. I can't do that one in my head. So 10 times 30 times sine of 30, and I get 150. So when we talk about which one exhibits a greater torque, this is still going to be a greater torque, even though we're pushing at an angle because the distance is far enough.